So this will be temperature notes number 2, and as always with these video lectures, you're going to take notes on scratch paper, and at the end of the presentation you will be given a notes quiz over this material where you can use the notes that you took. First of all, a little summary so far. Temperature is a measure of the friction between moving particles. We get that. But it takes energy to move, and if you add energies, things move more, create more friction, temperature goes up. And energy to move pretty much all comes from the sun. So let's piggybacking off of that. The higher the elevation, the lower the temperature because there's less air up there moving around. Water does not change temperature easily, so places near the water don't heat up and cool down as much as places away from the water. All stuff we've already covered, all stuff you should already know. But let's talk about the East Coast versus the West Coast, because as it turns out, they are not the same. We know that places along the coast do not change temperature very much because the water pretty much stays about the same temperature. So we have water out here on the East Coast and we have water on the West Coast, but there is a difference. As it turns out, places on the East Coast change temperature more than on the West Coast, and it has to do with which way the wind blows. For the most part, in our latitude, the wind blows across our country this way. So if you live over here on the West Coast, the air that is blowing to you is always coming over the Pacific Ocean. Pacific Ocean, big bucket of water, it doesn't heat up and cool down hardly at all. So that means places on the West Coast really never ever change temperatures that much because their air is always coming from the ocean, which is pretty much always the same temperature. The difference is out here on the East Coast. If you're on the East Coast, your air is blowing all the way across the country. So that air is moving across land. Well, in the winter time, that land is going to be cold. So you're going to give it a little bit colder air. In the summertime, this land is going to be hot because we know that all of this sand changes temperatures very easily. So in the wintertime, this land is cold, so the East Coast gets hit with colder wind. In the summertime, they get hit with a hotter wind, and their temperatures are hotter. Now, the East Coast doesn't change as much as an area in here because they're still close to the water. So they don't change as much as a place inland, but the East Coast changes temperatures a lot more than the West Coast, and it has to do with which way the wind blows. So that's a big conclusion here. The West Coast changes temperatures much less than the East Coast. Places on the West Coast of the United States have almost no temperature change year-round. They're pretty much the same temperature whether it's June or January. Places on the East Coast change a lot more from summer to winter because of the direction that the wind blows and it coming across land, not always coming across water. So now let's take a look at yesterday's classwork. Here's once again some basic review. Those first 3 questions all just review in terms of the relationship between energy and friction and where our energy comes from. This should have been what your map looked like. And what trend do you notice in the coldest cities? Well, it seems like all the coldest cities are up here. All the coldest cities seem to be in the north. Well, what trend do you notice in the hottest cities? Seems like our hottest cities all seem to be here in the south. So the question becomes, what explains that pattern? Why are all of the warmer cities in the south and the colder cities in the north? If temperature is caused by energy from the sun, aren't we all sitting under the same sun? Well, let's take a look at this graphic here, and you'll notice that here's the average temperature for Texas is 65, Oklahoma 60, 54. These are the average annual temperatures, and it seems like the further north you go, the colder it gets. And you know this to be true. What we need to explain is why. So thinking about temperatures. Temperatures are a measure of friction. which is from moving particles or moving air. And air moves because it's got energy to move. And all energy comes from the sun. So if all of the air is sitting under the same sun, shouldn't everything have the same temperature? Well, that's not necessarily true because the sun up north is not the same as the sun down south. And it has to do with the fact that the Earth is curved. Sunlight that hits the Earth at the equator is more concentrated. It's more in like a spotlight. All the sun's energy winds up in a very small area. As you go away from the equator, notice the sunlight gets a lot more spread out over a bigger area. So that means no one place gets as concentrated of sunlight. If you don't get as concentrated of sunlight, you don't get as much energy. Your stuff's not going to move as fast. You're going to have less friction, lower temperatures. Looks something like this. Think about sunlight coming down at a 90-degree angle. All the sunlight would be in an area this wide. But if the sunlight's coming in at a 45-degree angle, that same sunlight, because it's coming from the same sun, gets spread out over a much larger area. So the sunlight gets spread out. It's not as concentrated. Nobody gets as much energy. You're going to have less movement, less friction, lower temperatures. And I can demonstrate that for you in this little picture of Bart Simpson Lego figure sitting here. I've got a flashlight and I'm holding it straight over his head. And you look at how large the circle of light is from the flashlight. So all of the light is hitting inside of that circle. Well, then I move the flashlight and I hold it at an angle. Now notice that the sunlight is actually spread over a lot bigger area. So the same light is now more spread out. And the more spread out the light is, the less concentrated and the less energy any one piece of air has to move, so you're going to have lower temperatures. I can demonstrate that for you with the sun for real. Now here's two rulers, and I went out at solar noon, at the time when the sun was highest in the sky. And here I am, I'm in Oakland, California. And the sun is over here somewhere. Here's our happy little sun, and it is shining down on this ruler, and it makes a shadow. And you can see the shadow is about 4 inches long. The sun was pretty high up in the sky. As it's at noon, it's at its highest point. Well, the very next day, I flew to Hawaii, which is a lot further south. And I went out and did the same thing with these same two rulers, and you'll notice that there's almost no shadow because the sun was almost directly over the ruler, which means the sunlight was all very concentrated. It wasn't very spread out, which means you're going to have a lot more energy per area and hence a higher temperature. So what I demonstrated for you with those rulers is the concept of insolation. What we see in these diagrams, what we saw with the rulers, is that up here, the farther north you are, the more spread out sunlight gets. And that as you get closer to the equator and the sunlight is directly overhead, sunlight is a lot more concentrated. So you're going to have higher temperatures here where the sun is directly overhead. Places away from the equator where the sunlight gets spread out, you're not going to get as much energy because the sunlight's energy is spread out, and hence you're going to have lower temperatures. Think about the poles. You know it's cold at the North Pole and the South Pole because they just don't get enough concentrated sunlight, and the sunlight they do get is spread out because the Earth is curved, and this is the maximum curve away from the sun. That's the concept of insolation. To define insolation, it is merely the spreading out of sunlight due to the Earth being curved. And you can see that on this temperature map. You can see that the hottest temperatures are here in the middle where the sun is beating down on the Earth directly. Up here, you can see it's very cool because the sunlight is very spread out. They're not getting direct sunlight, so they're not getting a lot of energy from the sun, and hence they're going to have lower temperatures. So big conclusion here is the farther away from the equator, the lower the temperatures because sunlight is more spread out. So let's talk about temperatures in the seasons. So why do temperatures change throughout the year? Why do we have seasons? Where we have, hot times in the summer and cold times in the winter? Isn't the Earth always under the same sun, and the sun is what's causing temperatures? Now, if you ask most people, they would say that, well, in the wintertime, the Earth is closer to the sun, or farther from the sun, so it's colder, we're farther away. In the summertime, Earth gets closer to the sun, so we get more energy, it's going to be hotter. Now, you'd be partially correct, but in reality, the Earth is actually closest to the sun in January. It's a little bit further away in July. So that doesn't explain why we have lower temperatures in January than in July. Now, this whole idea of what a season is, the word season is derived from a Latin word that meant to sow, as in your crops. You sowed your crops. So seasons were based on when it was warm enough or there was enough sunlight for the plants to grow. So why does sunlight change throughout the year? It's the same sun. Yeah, we get a little bit closer and further away, but we are already seeing it's not enough to make a difference, and it doesn't explain our temperatures. It all goes back to this. If you've ever seen a globe shaped like this right here, where it looks like it's crooked, where it looks like the axis of rotation is right here. You spin the globe and it spins around that way. Well, that's how the Earth really is oriented in space. The Earth is actually tilted. And the primary reason we have seasons is because the Earth is tilted, specifically at 23.5 degrees to straight up and down. Well, how does that make a difference? Well, consider this here. We'll say this is our sun, this little lamp here. And here's my Earth. You see the picture down here. Here's the northern hemisphere. Here's the northern hemisphere. This is where we are in the northern hemisphere of the United States. Now, if you'll notice, our half of the world, there's the equator, our half of the world, our hemisphere is tilted more towards the sun, and this other hemisphere seems to be kind of tilted away. Well, that means our hemisphere gets a lot more light than the southern hemisphere in this orientation. Well, if you're getting more light, you're getting more direct sunlight, you're going to have higher temperatures. Look at it this way. I've outlined the two areas of the globe that are lit up by this light bulb, which represents the sun. And you'll notice there's a lot more area here being lit by the sun or the light bulb than down here. So if you get more sun, you're going to have more energy and you're going to have higher temperatures. This is what the world looks like on June 22nd. Now, if you'll notice, there's a lot, if you think with the equator right about here, there's a lot more dark areas down here in the southern hemisphere, and up here there is a lot more light. So you can see from this where the light and the dark separate, there's a lot more light in the northern hemisphere in this picture. Well, more light means going to be more energy, and more energy is going to mean higher temperatures. So we just look at this situation here where our hemisphere is tilted towards the sun. Well, our Earth doesn't stay like that. It moves around the sun on its orbit. At some point, it's going to be in this position. And we're going to skip ahead and look at what that means. So here we are. Here's our hemisphere now. This is the northern hemisphere where we are. You notice now we're kind of tilted away from the sun, and the southern hemisphere is more pointing towards the sun. Well, that means the southern hemisphere is getting more light than we are. If they're getting more light, more energy, they're going to have higher temperatures. And you can see that where I've illuminated on the globe, this here has more light. And this has less light. Well, light is energy from the sun. So if you have less light energy, you're going to have lower temperatures. So on December 22nd, here's that boundary between light and dark. We'll put the equator right about in here somewhere. You notice there's a lot more dark up here at December 22nd, and you know that to be true. You know that at December 22nd, around Christmas time, it gets dark really early. The days are very short. We're not getting as much sunlight, and we tend to have lower temperatures. Now, what about the points in between? Here is our hemisphere tilted towards the sun, and here's our hemisphere tilted away from the sun. So this would be like our summer, because we're facing towards the sun, getting a lot of sunlight, long days, warmer temperatures. And this would be like winter, where we're tilted away from the sun and we're not getting as much sunlight, and it's going to be shorter days and colder temperatures. But the Earth is also going to move along its orbit. So what's true when the Earth is here and here? So when the Earth is halfway in between, neither hemisphere gets more light than the other. And we have what's called an equinox, or a day when both hemispheres get equal amounts of sunlight. On March 22nd, you can see this. Notice the day and the night. There's just as much dark and light in both hemispheres. Here's my equator, roughly in here. And you notice the dark and the light are the same for both hemispheres. Equinox, meaning equal or equal light. So both hemispheres get about the same sunlight. Now that same thing is going to happen in the fall. There's a day in the spring, in March, where we have an equal amount of sunlight between the hemispheres, and there's also a day in the fall, or in September. In the wintertime, because we're tilted away from the sun ends up being much lower in the sky than it is in the summertime. And that angle of the sun is going to determine how much sun's energy you get and how concentrated it is. Obviously, when it is lower in the sky, it's going to get much less energy than when it is high in the sky. So, summertime, more concentrated energy. Wintertime, much less concentrated energy. So, when the sun is directly overhead, remember, the higher the sun is in the sky, the more concentrated the sunlight. If the sun is lower in the sky, sunlight gets spread out and you don't have as high a temperatures. So, in the wintertime, the sun might only get to here in the sky, and that sunlight is going to be spread out because the sun's low. In the summertime, when the sun is high in the sky, all the sunlight is coming to you more directly, it's more concentrated, you're going to be hotter. So what would happen if the Earth wasn't tilted on its axis? If the Earth wasn't tilted on its axis and it was just spinning straight up and down like this, you wouldn't have any difference in sunlight throughout the year. All of your days would be exactly the same length. All of your temperatures would be always the same. You would have no seasons because sunlight would stay the same every day of the year, which also means your temperatures wouldn't change from summer to winter. This diagram is going to be referenced a lot, including on the notes quiz. And I would suggest that you make yourself a rough sketch of this, where you have the sun in the middle, and we have the Earth as it's moving around the sun, moving this direction. And you know how the seasons work. We're in summer now, and at some point we will be back in summer once the Earth comes back around the sun. We have fall every year at the same time. We have spring every year at the same time, because the Earth is constantly going from A to B to C to D and then back to A again. So let's talk about what these specific dates mean, because that is a very special day, that's a very special day, and so are these two here. Position A, and I'm going to talk about everything in terms of the northern hemisphere, because that's the hemisphere that you and I live in. So, northern hemisphere. In this case, the northern hemisphere is pointing away from the sun. That particular day has a name. It is called a solstice. A solstice is a day where a hemisphere is tilted the most either towards or away from the sun. That's an important definition by itself. What is a solstice? It is the day where a hemisphere is tilted most towards or most away from the sun. Well, in this particular diagram, here's the sun. The northern hemisphere is pointing away, so that would be the winter solstice. It happens about December 22nd, and that is also called the first day of winter. That is when winter begins, at this one particular day when our hemisphere is pointed most away from the sun. It's our shortest day of the year. We get the least amount of sunlight, and that's what starts winter. So the Earth's going to continue to move, and 6 months later, it's going to be on the other side of the sun, and our hemisphere here is now going to be facing towards the sun. Well, that is called the summer solstice. Remember, a solstice is when you are tilted most towards or away from the sun. In this case, we're pointing towards the sun, so that is the summer solstice. That is the day that summer begins, on or about June 21st or 22nd. That's when we're getting our most sunlight. That's when our days are longest. That's when we start summer. Now, position B. We were over here at A, and we've gone over here to C. This was winter, and we're going over here towards summer. Well, what's in between winter and summer is spring. When neither hemisphere is tilted more towards or away from the sun, they both get the same amount of sunlight. The same or equal amounts of sunlight is called an equinox. It happens about March 20th of every year, and that is what we commonly call the first day of spring. It's the day when both hemispheres are getting about the same amount of sunlight, equal equinox. The other position on the other side of the sun is also an equinox, but this time it's called the autumnal or the fall equinox, and it's the first day of fall, on or about September 22nd or 23rd. So right now, we are still in summer, and especially now here in Georgia, it still feels like summer, but fall doesn't officially begin until about the third week of September. It's not so much about the temperatures, it's about the sunlight. And on that day, that's when we will get the same amount of sunlight as the southern hemisphere, and our fall season will start. Now, you might have heard that the opposite hemisphere has opposite seasons from us. And that's because if you look, the northern hemisphere, when we are tilted away from the sun, the southern hemisphere is tilted towards. So when we start winter, they start summer. When we start spring, they start fall. When we start summer, they start winter. The seasons are always opposite in the northern to the southern hemisphere.